Our next speaker is Ian Burton from the National Research Council, Canada, and he's going to be talking about the analysis of lignins using 31P Benchtop NMR, quantitative assessment of substructures, and comparison to high-field NMR. And we got a little taste of that in Susie's talk, I guess, and I'm interested to find out where all those phosphoruses go. So, so take it away.
Thanks for the opportunity to talk about this to the organizers of the IVEN NMR, and thanks in advance to my colleagues at Nanalysis for working with me on this and seeing the first few talks, first few presentations sort of reminded me of when I first got involved in NMR spectroscopy back in the late 80s. The first spectrometer I sat down to was a Bruker MSL 100, 100 megahertz spectrometer. The chemistry department at McMaster had a brand new 500, but they weren't about to let a first year grad student loose on that one. It just shows that we've sort of come full circle. But in the intervening, 36 years now, we've learned quite a bit about NMR and how to make it more sensitive, more selective, and quantitative. So the first, I'm going to first talk a bit about quantitative NMR itself before I get into the Lignins stuff. So NMR is inherently quantitative, and in terms of analytical spectroscopic techniques, I think it's probably the best quantitative method, but then I'm probably preaching to the choir here with that. So in essence, the signal strength is directly proportional to the number of magnetically equivalent nuclei giving rise to that signal. We've used this all the time when we do structural elucidation and looking to see how many protons are associated with each site. Because the number of protons is directly related to concentration, we can come up with basically a formula for measuring the molar concentration of a compound in solution relative to either an internal or external standard. So the intensities, the integrated intensity is proportional to the concentration times a proportionality constant. And when comparing a standard to an analyte, it can only be done when the Ks are equal. And these are the quantitative conditions that we talk about. So uniformity of pulse angle, taking into account relaxation, probe Q, or tube geometry, consistency in data processing and integration. But when we do, I mean, this all applies to low field and high field. And when we do external standard quantitative NMR, there's far more conditions that you have to take into account. When we do internal standard NMR, a lot of these conditions are already taken into account. Things like probe Q and tube geometry. And just shown here is a quantitative spectrum at 60 megahertz of tadalafil versus a internal standard. DMT is the internal standard. And one of the things that you can see in this spectrum is that we've got two nice singlets, well resolved, and that basically allows us to quantitate one against the other. So the internal calibrate method, there's a few conditions we have to take into account. You've got to ideally have a high purity internal standard. Ideally, it shouldn't overlap with other signals. Should be soluble, no chemical interferences. Typically, it's weighed in the same vial. A lot of times, the internal standard may be added to the solvent used in bulk so that you have a consistent internal standard measure in your solvent. This is generally how we do it, internal standard NMR, our method in our lab. So in general, you can then come up with a formula if you want to know the mass that you have in there, knowing the formula weight, purity, knowing the purity of the internal standard is important, and very easily come up with a molar or a mass amount. One advantage that NMR has over other techniques, I should mention, is that it has a uniform molar response. That's what makes it such a what I consider the best technique. In that you don't have to have, as an internal calibrant, you don't have to create a calibration curve or have a similar or the same compound to create a calibration curve. You can use an external standard or an internal standard, any chemical type. And as long as you adhere to quantitative conditions, the two are comparable. So key considerations, just to reiterate, accuracy, weighing, gravimetrically, you're generally comparing the NMR signal of interest to a gravimetrically determined standard, either internal or external. So the mass has to be determined accurately. You have to know the purity and the volumes that you're using primarily for external standard NMR. Acquisition parameters, again, consistency in all of this, but since we're integrating the spectra, you want to have good definition of your curves. So number of points is critical. Since you're doing a sum basically of the points, the more points you have, the better your sum is going to be. Repetition time, adequate spectral width. It's not so much that used to be more important back before digital filtering and things like that, but generally you don't want to be trying to quantitate anything that's too close to the edge of your spectrum. The key, always critical, is relaxation time, and typically you want to wait 5 to 7 times your longest T1. With the lignins, we use a relaxation reagent. So we're using chromium acetylacetate as a relaxation reagent to reduce the repetition time. So proton NMR isn't the only thing we can do quantitation on. We've seen examples of C13. Other nuclei like fluorine and phosphorus have advantages in that they have a broad chemical shift range, or excellent dispersion. With a complex mixture like a lignin or foods or extracts of botanicals, things like that, the proton spectra can be extremely crowded, and it's very difficult to get clean integrals, even when you do things like deconvolution. But when you go to fluorine and phosphorus, generally you're looking at a nucleus that is in very specific chemical environments, and it's in you have a broad chemical shift range and excellent dispersion, so you can generally separate things better. So fluorine and phosphorus are the ideal ones because they're 100% natural abundant. They're spin 1/2. They have a fairly high gamma, so they're at a fairly high higher sensitivity than things like carbon-13 well, in this case, lithium. So for the lignins, phosphorus was the ideal one. Now, lignins don't contain phosphorus, so we have to add phosphorus to it. This gives us some selectivity in what we can look at in a complex biopolymer. So again, low field NMR versus high field NMR, generally you lose out in sensitivity and dispersion, but by going to something like phosphorus, it's 100% abundant. So if you've got a lot, enough sample, it's fairly easy to see a spectrum. Plus, you have a dispersion. The large dispersion of phosphorus overcomes a lot of the overlap that you would have in, say, protons. So this method for lignins is not new. It was developed back in the 90s by researchers at McGill for phosphorylating the OH groups of lignins. And we saw basically what a lignin looked like in the earlier presentation. But lignins are very important in the pulp and paper industry, are becoming important. Generally, in the past, they wanted to get rid of lignins in the pulp and paper process. It adds color to the paper, to the pulp product. And generally, what was done with it, it was extracted from the pulp and burned for heat to be used in the delignification process. But the nature of lignin, it's a complex heteropolymer. The monomer groups are phenols, and as individual compounds, they could have very high value. Generally, these kind of compounds are derived from petrochemical sources. So, throwing this stuff out may not be there may be value to keeping it. And as a polymer, it's actually, lignin is responsible for the sort of structure of wood. The lignocellulose gives wood and those kind of things. They're actual structure, the strength of wood. So as additives to other compounds, lignins could be important to modifying or modulating the structural properties of other products like adhesives or resins and things like that. So generally, a lignin is made up of syringyl, guaiacyl, and synapyl groups, but they can be arranged in a lot of different ways and connected in a lot of different ways. And that's important to understanding the sort of properties of the lignin, the cross-linking, the amount of the different monomer groups, functional groups on the polymer. Now, one nice thing about doing NMR is the NMR nucleus, or the atomic nucleus, is a very sensitive measure of its local magnetic environment. So when we say add phosphorylate, something like this, we're basically adding phosphorus to where all the OH groups are in this polymer. That can give us changes or not changes, but the chemical shift of those phosphorus environments tells us something about the linkages and the other functional groups that are around it. So what we do is we've settled or the industry has sort of settled on a compound called TMDP. It's tetramethyl what is it? That compound there. I can never remember the name of it. But it's basically a phosphoryl chloride, which reacts with anything with an OH group on it. And what we see in the right here is the different environments that come about, the different chemical shifts that come about in the different environments. So in this region here, you've got aliphatic phosphorus, you've got or phosphatidyl groups, aromatic in here, and down in here you've got carboxylic acid groups. Water is always present in these things because this reacts with anything with an OH group. Any water that's around in the environment becomes or gets sequestered and reacted with in your solution, including water in the air. We do use that though, and it's always seems to be around in the samples. So we use that as actually a chemical shift reference. And our internal calibrant we use for this is cyclohexanol. So the range of these things is a fairly narrow range for phosphorus, between about 130 to 150 ppm. And pure compounds, you have very well resolved peaks. But in a polymer, you're going to get very broad, very broad features in the spectrum, but they can still be integrated. So this was all part of a round robin study with Canadian Standards Association, CSA group, in order to create a published method, standard method for the analysis of lignins. It was originally done at high field between 400 and 600 megahertz. Several labs got involved, and FP Innovations supplied us with 4 what are called known as standard lignins. The lignins that they've isolated in the lab using the various processes like the Kraft process, Organosolv, and the soda method for extracting lignins. And the different methods modify the lignin structures and the different sources. So at the top here, we have a softwood lignin. The bottom 3 spectra are hardwood. The bottom one is a softwood lignin. The top 3 are hardwood lignins. And we generally integrate over very broad regions. So we have our internal standard, aliphatic, carboxylic acid, p-hydroxyphenyl, guaiacyl, 4,5-syringel. These are different aromatic linkages. And by integrating these ranges, we get an idea of the proportions of the different groups that are in the polymer. Generally in NMR, we measure molar concentration, but because it's a complex polymer, we can't actually get a molar amount. So we express our results in the moles of that species per gram of total lignin. But you can see here how things change with the different types of wood, softwood versus hardwood, as well as the different methods. These 2 here are with a K in front are Kraft method, one for hardwood, one for softwood. But even within the different hardwoods, depending on the method, you get different proportions of different functional groups expressed. Okay. So we initially did this at high field NMR, 500 megahertz. But there's nothing stopping it from being done at low field. These are inherently broad spectra. So phosphorus, they have broad lines, but that shouldn't really hold us back when doing low field NMR. So what we have here is the Kraft softwood lignin, same sample at 1.4 Tesla and 11.7 Tesla. So 500 megahertz and 60 megahertz, and the same features are all there. The signal to noise is comparable, but this was run at 8 times the number of scans at low field as it was at high field, and we get a difference about a factor of 3 in signal to noise, which lines up with what you would expect with that field difference. But since and we do see some broadness in some of the sharper peaks in the Carbonell region, but since we're integrating over a broad range, that really doesn't really hurt us. And again, this is our water peak at 132.2 ppm and our internal calibrate here, which have similar or fairly sharp line shapes. Just to compare low field NMR, we had a comparison of the high field NMR. We see the same differences. This is basically softwood versus hardwood, and you see a big difference in the syringeal region and 2 different methods of doing hardwood lignins. The soda lignin uses a alkaline method to break down and delignify the lignocellulose, which tends to create a lot of carboxylic acid groups, especially in sort of small molecules. It tends to break down the polymer a little bit more, creating carboxylic acid groups than, say, organosolv or the Kraft method does. Now, when we compare the analysis between high field and low field, we did the softwood at 2 different number of scans, 128 scans for the and 256 scans for the high field, and 1K scans and 2K scans for the low field, just to get a feel for what effect signal to noise has and what's the lowest number of scans we could do. But in comparison with high field to low field, most cases, especially when you have good signal to noise in your integral regions, you get fairly good agreement between the high field and low field. It's when you get into the low amounts. So primarily the p-hydroxyphenyl, you're getting very low in your amounts, and your integrals are very the signal to noise of your integrals are very low. So you get very large differences between high field and low field. But in reality, we observed the same effect between the different labs, and in the multi-lab, the round robin study, in that it was very difficult even at high field to get consistent results for p-hydroxyphenyl. So the difference of 19% is actually pretty close to the variance we were getting in the high field results. But when we have higher signal and better signal to noise, we generally get better agreement. And so, just in conclusion, I'll leave some room for questions. 4 lignins were analyzed. The 4 different standard lignins. The comparison between low and high field shows that the method at low field gives comparable results, and providing you can get adequate signal to noise. The difference in time between high field and low field is about a factor of 5, or a factor of 8, actually, between high field and low field. So a few hours to get a spectrum. However, the results are comparable, and when you compare the arguments that were made in earlier talks about the investment and the potential availability of low field NMR, it still makes sense to do this at low field. And the longer acquisition time, some of these compounds, it's been in some papers, it's been suggested that the phosphorylation compounds are not that stable over time. During this, we found that that really isn't an issue over these kind of timescales. Just running these things at high field over long periods of time, we haven't noticed significant degradation of the internal standard or the lignins. So time really isn't a consideration in that effect. But it also, I mean, lignins work well, but there's other types of forestry products or biorefinery products that could be analyzed this way as well. Things like proanthocyanins, pectins, those type of compounds could potentially be analyzed in the same manner. So that's some future work that could be done with this. So in conclusion, I'd like to thank my my colleagues in all of this, Matt Leclerc, Suzanne, Juan at Analysis, for the low field NMR work, and Matt's time on the CSA working group. Michael Peloglu at FP Innovations, who is doing low field NMR on the lignins and supplied us with the standard lignins. Fanny Montoya Rivera at NRC in Montreal, who has done a lot of work with this method over the years, and was on the committee with me. And Melanie Peneton at CSA Group, who was the lead on the lignin working group at CSA, and led the development of the method. Any questions?
Questions?
I had a question about the stability of the phosphorylated samples.
Mm-hmm.
Can you talk a little bit about the sample prep and whether or not you use like a J-Young tube or something so the sample would stay water-free longer?
Yeah, so the samples and the reagents they're all stored in under desiccant in vacuum desiccators. When we went to do the analysis, to do the reaction, I did everything in a glove bag that was purged with dry nitrogen. And generally, I made up each sample right before I was ready to analyze it. So I didn't make up bulk samples and have them sitting in the spectrometer sample changer for a long period of time. Water is your enemy here. I tried doing this with, say, a curtain of nitrogen gas. And as soon as you open the bottle of the reagent, it just basically sucks all the water out of the air and turns white, and you get basically no reaction. So it is critical doing this under dry conditions. I found using a glove bag or a glove box works best. But in terms of stability of the compounds themselves, as I said, there's been some papers out in the past that have said that, that the internal standard, or at least the cyclohexanol internal standard, isn't that stable. But it's stable enough over days that if you run these things right after you make them up, you still get quantitative results. And I've seen this by basically running the same sample over weeks at a time.
What kind of NMR tube did you use?
Oh, we just use high throughput tubes for this. We didn't use high precision tubes, so fairly inexpensive 5 millimeter high throughput NMR tubes.
And regular plastic.
Oh, the caps? No,
Yeah.
no, the caps we used Teflon caps, and basically wrapped in a Teflon cap with Teflon tape to reduce evaporation. So the solvent system was also, we use chloroform, deuterated chloroform with protonated pyridine. The pyridine is there to scavenge any chloride that gets produced and reduces the acid levels after the reaction. So to keep things from evaporating, we use Teflon caps with Teflon tape.
Thank you.
Our next question, is coming from a viewer online.
This is a very specific question from Michael Respondek. Do you recall what is the T1 time of the internal standard phosphor derivative of cyclohexylane, and what solvent do you use?
Well, the solvent is the chloroform pyridine system. We added chromium acetylacetonate, which reduced the T1 down to less than 2 seconds of the cyclohexanol added phosphorylated cyclohexanol. So we had a repetition time of about we could get away with a repetition time of about 10 seconds. The T1 without the relaxation reagent, I can't recall off the top of my head. We measured it with the relaxation reagent, and it was in the order of below 2 seconds with the amount we used.
Okay, thank you. No, more questions from the group here. Okay, well, thank you again for your talk.
No more questions? Okay, I'll stop sharing.
Yep, no more questions. Thank you.
Okay, great.